Today we will be learning about the most important rearrangement in mass spectrometric technique. Under mass ionization conditions, compound will undergo McLafferty rearrangement. The compounds especially which are having carbonyl group and gamma hydrogen or benzene ring and gamma hydrogen. So we have a carbonyl group. This is alpha, beta and this is gamma. And we have a benzene ring. We have an alpha, beta and gamma hydrogens. So the requirement for McLafferty rearrangement is presence of either the carbonyl group or benzene ring and presence of gamma hydrogen. Let's see the specific example. You consider this carbonyl compound. Here we are having alpha, beta and gamma hydrogen. Two gamma hydrogens are there. One of the hydrogen is shown. McLafferty rearrangement is the rearrangement which involves the formation of cyclic six-member transition state. So gamma hydrogen is numbered as 6, gamma carbon is 5, this is 4, 3, carbonyl carbon is 2 and carbonyl oxygen is 1. And it involves cyclic six-member transition state and there will be a transfer of hydrogen with the bonded pair of electron to oxygen followed by subsequent electron transfer and it leads to the formation of the compound. So this double bond O will become as OH and we'll be getting double bond over here and already one single bond is here plus olefin. So initially we are having a radical cation because under mass conditions the fragment that is generated will also be a radical cation. So under mass condition, we will be getting a mass corresponding to this particular fragment. In the same, instead of a carbonyl group, if we are having a benzene ring and a gamma hydrogen, alpha, beta and gamma hydrogen, then also McLafferty rearrangement is observed. So we have a benzene ring over here and we have alpha, beta and gamma hydrogen. And gamma hydrogen is 6, gamma carbon is 5, 4, 3, 2 and 1. And we all know benzene ring also has hydrogen in it. So there will be a transfer of hydrogen from 6th position to 1st position along with the bonded electrons and there will be a subsequent electron transfer. So what we will get? We will get benzene ring in which these two bonds are not disturbed and this becomes double bond CH2 and here already one hydrogen was there. Now one more hydrogen got transferred here. So plus CH2 double bond CH2. So under mass condition this will be a radical cation. So this fragment will also be a radical cation. So we will be getting a mass corresponding to this particular fragment. Now we will look into few questions asked in examinations. This question states that among the isomers of C10H14, the isomer that can be identified uniquely by mass spectrometry alone is. Now we can see here benzene ring is there and we can see some alkyl chain. Let's look where we have gamma hydrogen. Here we have only alpha and beta. Here we are having alpha, beta and gamma. Whereas here again alpha and beta. Here also again alpha and beta. So the McLafferty rearrangement is shown only by the compound where we are having a gamma hydrogen. So the correct option is B. Now look into this question. Among the following, the compound that gives base peak at M by Z 72 in the EI mass spectrum. EI is electron impact, which is a hard ionization technique which is useful for the study of small molecules like our organic molecules. Now we will look here. Here we can see all the compounds have a carbonyl group and they are having alkyl chain. So it gives an indication that it could be a McLafferty rearrangement. So under mass condition, all the compounds will form radical cation. Now we have to look for the presence of gamma hydrogen. So alpha, beta and gamma we have, and this is delta. And in gamma we have two hydrogens, only one hydrogen is shown over here, so that we can see the McLafferty arrangement. So this is 6, 5, 4, 3, 2 and 1. So from 6th position, hydrogen is getting transferred into position 1, followed by subsequent electron transfer. So compound 1, under mass condition, it will have formed radical cation. So 1 will give, this becomes OH, and this becomes double bond, and already substrate is there. Plus we will be having an olefin. So this will be our radical cation. Let's calculate the mass. How many carbons we have? 1, 2, 3, 4. So 4 carbons we have, and hydrogen CH3, CH3 6, 7 and 8. So 8 hydrogens, and we have 1 oxygen. And we know each carbon has the mass of 12. So 12 into 4, that is 48. And each hydrogen is having the mass of 1. So 8 hydrogens, and the mass of oxygen is 16. So when we add all these things, we are getting 71. Okay. Now under mass condition, this is the mass corresponding to this fragment. Under mass condition, the compound can abstract proton. So this corresponds to mass m. So under mass conditions, it will abstract a proton, so it will become as m plus h. So 71 plus 1, so it will become as 72. So option 1 gives the m by z value as 72 under mass conditions. Now you consider the compound number 2. Here also we have alpha, beta and gamma carbons, and hence gamma hydrogen. So one of the gamma hydrogen is this one. So the electron transfer will be like this. So what we will get? We will be getting OH and then double bond. Under mass condition, it will be a radical cation, because even this would have been a radical cation. Plus we will be having a olefin, right? Yes. Now for this one mass, we will check it out. How many carbons are there? 3 carbons. And how many hydrogens? 3 plus 2, 5, 5 plus 1, 6. 6 hydrogens and 1 oxygen. So mass will be 36. 12 into 3 is 36 plus 6 plus 16. So the mass will be 58. So m by z of 58, it will give the fragment which is having the m by z of 58. Now consider this one, alpha, beta and 2 gamma carbons are there, 2 different types. This is gamma and gamma prime. Let's see in each of the gamma hydrogen, what is the product that we are going to get. So this will migrate over here, this will migrate here, and this will migrate here. So we will be getting OH double bond. This is what that we will be getting, plus this fragment we will be getting. We can see this fragment is same as that of the fragment which we have got from compound 2. This is again C3H6O. So again the m by z will become 58. This is what that we have got by considering this gamma hydrogen. Even if we consider this gamma hydrogen, the same fragment we will be getting of mass corresponding to m by z of 58 only. Now we consider this compound. This has alpha, beta. Here also this has only alpha and beta, no gamma hydrogen. So no McLafferty arrangement in this particular compound, and we can't show any fragmentation which corresponds to the mass of 72 as well. So out of all the 3 options, in the first one we got m by z of 71. In the second case we have got 58. In the third case we have got the m by z as 58. So the close to 72 is 71. So under mass condition it would have taken up one more proton, giving the formation of 72. So 71 plus for mass of one proton is 1. So it will become 72. So the correct option is 1. Now consider this question which has been recently asked. Now here the question states that this is in multiple selection questions. More than one answer could be correct. So compounds that show an intense peak at m by z 120 in the electron impact mass spectrum. We have to find out. Now all of them are carbonyl containing compounds. Some of them have gamma hydrogens. So we can think of McLafferty rearrangement. So here you are having alpha, beta, and this is our gamma, right? And this is one of the gamma hydrogen. Electron transfer will be like this. So we will be getting benzene ring. This becomes OH and this becomes double bond. Under mass condition, this will be a radical cation, and hence we even will be getting this as the radical cation, and byproduct will be a olefin. So we will be getting double bond like this. And we have to calculate the mass for this one. So how many carbons we have? 6, 7 and 8. So 8 carbons, hydrogen 5 over here, 6 and 7, 8. So 8 hydrogens and 1 oxygen, that corresponds to 12 into 8 plus 1 into 8 plus 16. So we will be getting 96 plus 8 plus 16, that corresponds to 120. M by Z of 120 that we are getting. Now you consider this particular species. Here again we have gamma here. Alpha, beta, both are gamma, both are equivalent. So this is one of the gamma hydrogens. So McLafferty arrangement will be like this. So we will be getting benzene ring, OH, and then this will become double bond. The fragment is same as in the previous case. So even here the mass will be same because fragment is same, mass will be same. So here also byproduct will be a olefin again, right? Yes. Then here also m by z corresponds to 120. So already we have got two options. Now we have to look for the other options. Here we can see only we have alpha CH2, and here also we don't have any gamma hydrogen. So now we can check by any other means we will be getting the options correct. And you can see the mass of this particular compound as such is 152. Mass of the compound as such is 152. We can see it's a carboxylic acid. So carboxylic acid, there will be complete loss of COH that accounts for the mass of 45. So 152 minus 45. That corresponds to mass of 117. But in the question it is asked us mass of 120. So this could not be the correct option. Now if you consider option D, it's an ester compound, methyl ester. Methyl ester, it involves the formation of loss of OCH3. It involves the loss of OCH3, and even this is a phenolic compound. Phenolic compound involves the loss of hydrogen. So OH hydrogen will be lost. So the mass of this compound is also again 152. And if OCH3 is lost, so minus OCH3, and we have to consider for minus hydrogen. And OCH3 mass corresponds to 31 and hydrogen mass corresponds to 1. So 152 minus 32, that also accounts for 120. So even this option will be correct. So for this one, the correct options are A, B, which we have found by means of McLafferty arrangement, and D, because it is a methyl ester. Methyl ester involves the loss of OCH3 under mass condition, and even phenol involves the loss of hydrogen. So the correct options for this question is A, B, and D, multiple selection question. And let's consider this question. Here the question states that the m by z value of the detectable fragment formed by McLafferty-like rearrangement. Why it is called McLafferty-like rearrangement? Because we have seen McLafferty rearrangement in the case of carbonyl compound and benzene ring, but here we are having nitrile group. So here this is we have to treat this like a carbonyl compound, and we have to write the product of McLafferty rearrangement. Now here again requirement is gamma, alpha, beta and gamma. This gamma is having one hydrogen. Now we will write it in such a way so that we will show the cyclic 6-member transition state. So nitrile is C triple bond N. We have alpha, have beta, and we have gamma over here. In gamma we have two substituents and one gamma hydrogen. So this is alpha, beta, and this is gamma. So this is number 6 and this is number 5, 4, 3, 2 and 1. So hydrogen is transferred over here with the bonded pair of electron, and these electrons are getting shifted over here and this is getting transferred over here. So what we will get, we will be getting C, it becomes double bond N and H, and this also becomes double bond. So under mass condition it will be a radical cation. Okay, originally even this will be radical cation under mass condition. Then byproduct will be, we have this and this becomes double bond, and this is the olefin that which we will be getting. So we have to calculate the mass corresponding to this one. So how many carbons it has? It has got 2 carbons and it has got 1 nitrogen, and hydrogens are, here we are having 2 and here it is 1. So 12 into 2, 24, and nitrogen is 14, 3 hydrogens. So when we add everything, we will be getting the masses 41. So the correct answer is M by Z of 41. This is how we can use McLafferty rearrangement to get the products. Thank you for watching. Happy learning.